Hey math fans, we're on section 2.7.1. Let's get started. This section is called building functions from context. And if you ask me, this is really what math is all about. We're trying to come up with a function to a set of data, and most likely what we'll do is we'll take a graph or some other scenario and we'll put all the information into a table, and it's going to be put into one of these forms, either a linear or an exponential. And the big thing that we're going to be looking for is whether or not it has a common ratio, which is also going to be known as the base of our exponential. If it doesn't, then we're going to probably have a common difference, which is just going to lead us to our slope. Example 1, the starting balance of Anna's account is $1,250. She takes $30 out of her account each month. How much money is in her account after 1, 2, 3 months? Find an explicit function to represent the balance in her account at any month. So the term explicit means that we can actually have a function where we can substitute in 1, 2, 3, and we can get an exact amount, as opposed to recursive where we have to look at the previous month and just add or subtract or multiply or divide. First step is always make a table. As you can see, I've made a table right here and I've substituted those values in. As you can see, the values are decreasing by 30 every month. And we will start calling this a common difference. And if it's the same amount every time, this common difference will mean that this is going to be a linear function. So if it's linear, all we really need is the slope and we need the intercept. The slope is pretty easy to see from a table because it's just going to be the change in y, which is negative 30, over the change in x, which is increasing by 1. And as you can see, it's going to be negative 30 over positive 1, or just negative 30. But how do you get the intercept? Well, the intercept in this particular case is pretty easy because it's whenever x is equal to 0. However, let's say you didn't have that value. Well, you could use 1, 1220, 2, 1190. Any of those values could be substituted in for the y and the x values. And as you can see down here, what value for b would you get if you, let's say, substituted in 1, 1220? Well, remember the y value is the 1,220. The x value is 1, and you solve for b, and you get 1250, which is the same as what was in the table. So your final answer is f of x is equal to negative 30 x plus 1,250. Consider that the first figure in the following diagram has two 180-degree angles, one on each side of the line segment. Each of these angles is bisected or cut in half. And then what we're going to do is start counting the number of angles. So as you can see, figure 1 has 2 angles, two 180-degree angles. Figure 2 has 4 angles. Figure 3 has 8. Figure 4 has 16. We're going to come up with a function to represent the scenario. As always, make a table. As you can see, I've done so here, and we try to find a pattern. Now notice, is this increasing at the same rate or decreasing at the same rate like last time? Well, no, because look, it's increasing by 2 here. Now it's increasing by 4. This is not going to be linear. This particular function is going to be exponential. We can find a common ratio by dividing the y value, or the f of x value, of the current term. And if we divide it by the previous term, we get that common ratio. So 4 divided by 2 is 2, 8 divided by 4 is 2, 16 divided by 8 is 2. Please check at least 2 of these just to make sure that it's exponential. So this particular scenario is a little bit tricky. It's not going to be a continuous function. It's going to be more like a sequence, which is this format down here. If it was a continuous function, we'd be using this one. However, if you can remember that your domain is going to be counting numbers, you could also use this function up here, but I'm going to start us off with how would you use the sequence function, because really there is no figure 0. So we're going to be looking in terms of the first term. So as you can see here, the first term is 2, and I've kind of highlighted it right there. Notice when we're using this format, it's not x in the exponent, it's x minus 1. We're using the previous term. So just be careful with that. I'll show you using the other function as well, but it's going to be x minus 1 in the exponent. The common ratio, or the base, is going to be 2. We've already figured that out. So all we need to do is solve for k. So choose any ordered pair to use. For this particular example, I chose 3, 8. So 8 goes in for y, and then 3 goes in for x, and you solve for k, and you get 0. Final answer is going to be 2, the first term, times 2, which is your common ratio, raised to the x minus 1 power plus 0, and you don't have to write the 0. So what if this was a continuous function and it wasn't that we were bound by figure 1, figure 2, figure 3, and we could figure out what the intercept was? Well, then we could use this function format. Notice that it's just to the x power. We would be using the y-intercept as our beginning term, just like any other exponential function. So your first term is going to be 1, because if we are multiplying by 2, we will be dividing by 2 and in the opposite direction. And then we solve for k. Again, I'm using 3, 8. You could use any one of these ordered pairs. 8 goes in for y, 3 goes in for x. Solve for k, you still get, you guessed it, 0. So your final answer is f of x is equal to 1 times 2 to the x plus 0, or you could just write it like this without the 0 or the 1. But Mr. Porter, those are 2 completely different functions, aren't they? Well, actually, no. If you were to create a table of x and y values, they would be exactly the same function. Just this one is for if you only have sort of a sequence for your domain or counting numbers for your domain. And this would be for a continuous function. But notice I have graphed and Desmos, both functions, and they map on top of each other. And that's going to do it for this section. We'll see you in class.